So now I give you two systems of equations. And the two systems, if you look at, they are in a similar form, right? Except the first system, the coefficients, I use A, B, C, D instead of specific numbers. So in the first system, if I represent using some positive values here, A, B, C, D, in this first system of two equations, and A, B, C, D are coefficients. And they're positive. But if A is positive, then negative A will be negative. So we can see that you see a negative A. And here, if D is positive, then negative D will be negative. So this equation is a generalized version of the second one. So the second one is just a very specific set of two equations. Here, how specific? That means if A is 1, right? In the first system of equation will become a very specific one. When A is 1, then you get this term, negative 1x. If B is 1/10, then you get this term, 1/10 times xy. If C is 1, then you will have 1 times y. If D is 1/5, and then you will have here 1/5 times xy, and with a negative sign in the front of D. So we just want to see that the two systems are the same, except the first set of two equations is a generalized version. Yeah, the second one is a very specific set of two equations. So that is when A is 1, B is 1/10, C is 1, and D is 1/5. Then we will have the specific system. And we have already discussed the specific system. Now I want to just look at the general system, and then what are the constant solutions. So for the general system, if we are looking for the constant solutions, then very quickly we simply assume, right, our solutions x, y functions being constants. So immediately the derivative of x and derivative of y will be 0. Therefore, we have derivative of x is 0, derivative of y is also 0. So the second equation becomes cy minus dxy, with ABCD being constants, being positive constants. So as soon as you look for the constant solutions, the derivative will become zeros, and they will disappear from the equations. And then you are simply solving an algebraic system. That means you just solve this system of equations without derivatives. And then let's quickly solve it. So this system, once we go ahead, right, we just solve the general system. then we can see the first equation after I factor out x, the common factor, then I get negative a plus negative a plus by. And then the second equation, after I factor out the y, then I get c minus dx. So then the two equations, then we can solve. So if for the first equation to be true, then x either the first factor is 0 or the other one is 0. So we know that if a product of two quantities are 0, right? Either the first quantity is 0 or the second quantity is 0. So that means either x is 0 or the other one is 0. So that means we can find y, which is a over b. So for the second equation to be true, either that means either the y is 0 or c minus dx is 0. So one of the two factors must be 0. So that means either y is 0 or x is c over d. So therefore, we have found two constant solutions. So two constant solutions. The first constant solution, let me write in a bright color so we can see it well. So that first constant solution, x is 0, y is 0, right? So let's write it in this ordered pair. The second constant solution, x is c over d, y is a over b. So now let's, for the system, we worked on this general system. So we have found two constant solutions. X is 0, y is 0. The other constant solution is x is c over d, y is a over b. Yeah, so that means if you can find always two constant solutions for this type of system of equations, then quickly you can apply the formula for this specific system where A is 1, B is 1/10, C is 1, D is 1/5. Then you can quickly know the constant solution, right? So when we substitute A, B, C, D, then we can immediately conclude for this particular system, the constant solutions either 0, 0 or C over D, which is 5, A over B, which is 10. So yes, so we have solved a general system, which is giving us a formula to find constant solutions. So the formulas are just this, right? But this constant solution is not so interesting. It's a trivial solution. That means x is 0, y is 0. So if for a population model, that means neither the predator nor the prey will exist. That means when they do not exist, then everything is 0. Then of course they satisfy the first equation and second equation. That's a trivial solution, which is not so interesting. But if A, B, C, D are positive, then I have predator population X, right? And prey population Y. And they both exist and they do interact with each other. And then this positive solution is more interesting. So now I want to show that using XY plane. So let's draw some non-constant solutions. So we know that we have this constant solution if we show in the XY plane, and we can see the trivial solution as 0, 0, which is a point, and another constant solution. So let's remember, this is one constant solution, the other constant solution. So yeah. And for the specific system, the constant solution, yeah, the trivial solution is always a solution. And remember, for the specific system, we have 510, right, with ABCD given as above. So we can easily show the two constant solutions. So here, if I just point at here, so this is 1 and 5, 10. Suppose x is 5, y is 10, right? 5, 10. Then I can pick, this is a 5, 10, another constant solution. So for this constant solution, we should, yeah, so this is what I'm trying to show, that it is a point, right, in the XY plane, because T is implicit. So it is a point, each constant solution. So we have two fixed points. Yeah, so those, but according to the Volterra's first law and second law, we know the constant solution values. Let's write it specifically. X equals 5, y is 10, especially this constant solution, tells the average population for non-constant solutions. Suppose we have a periodic solution. Let me draw a curve. Suppose it's not constant, and it is a periodic solution according to Volterra's laws, that we can actually, for example, show a closed curve, right? Suppose we have a closed curve, and then from this point, and we try to draw like one horizontal line, one vertical. It's like 5, 10 as a like new origin. And then suppose this is a 5, 10 here in the middle. And then let's look at just one quadrant, which is in this upper right. So if your x, y in this area, in this part, so that means x is bigger than 5. Why? Because the x value is on the right side of the point 5, right? So x is bigger than 5, and y is, so I'm looking at this part. Yeah, so this part of the curve. So this curve obviously is moving with time. So that means it's not a constant solution, right? X is changing, Y is also changing. So it's not a fixed point. So Y is bigger than 10 because it's higher than 10. So I just restrict my attention to this part of the curve, which is a periodic solution of the system. So let's look at what happens for this part. So remember the equation, x prime, y prime. Remember the equation? So the equation, if you go backwards, you will see that particular system. Yeah, negative x plus xy over 10, the positive y minus xy over 5. So let's write it here just for convenience. So I'm going to write that like factored form, right? Plus xy over 10. No, x is already factored out. So I have only y. So so let's take out this, and then we have y only over 10. Okay, for the y derivative, I factor out y and minus x over 5. Because this way is easier to see. And for our discussion purpose, we are going to look at when x is bigger than 5, what is happening? When x is bigger than 5, this is certainly positive, right? This is bigger than 5, positive. But y is bigger than 10, so y over 10 is bigger than 1. If it's bigger than 1 minus 1, it will be bigger than 0. So both factors are positive for this range of x, y values. So that means our x derivative is positive. So we have come to the conclusion that this x derivative is positive. And let's continue. We still restrict our attention to this sector. So let's see. If x is bigger than 5, this part, so x over 5 is bigger than 1. Bigger than 1. So 1 minus something bigger than 1, negative. This is negative. But y is bigger than 10, right? So y is positive. So positive times negative, negative. So then immediately we know that y derivative is negative. So what does that say? That means if x derivative is positive, x is increasing. So we can know that the arrow must be in this direction. So this is the direction. I want to add this arrow. That is the direction of the orbit. So a periodic solution is moving. Yeah, I can make it a little cleaner. So then we can see it's moving in the clockwise direction. As you can see, if moving in that direction, x is becoming bigger and bigger, right? So it's x is getting bigger and bigger, larger than 5. But y, what's happening? When it's moving in that direction, y is going downward. So y is becoming smaller and smaller. So that agrees with so the y derivative is negative because y is decreasing. So we can see from the signs of the derivative function. So that tells us when x derivative is positive, that means x is increasing. When y derivative is negative, that means y value is decreasing. So if x is decreasing and x is increasing, right? Y is decreasing. So that shows the flow in this quadrant. Yeah, it is moving in this direction. That's X increasing, but Y is decreasing. You see, moving lower. So yeah, so similarly, you can look at another quadrant. So for example, after you move and go beyond that quadrant, then we can focus our attention to this quadrant. So this quadrant, then we can do a similar analysis. In this quadrant, that means X is still bigger than 5, right? X is still bigger than 5, but Y is less than 10. So then we can have some discussion. So let's go to this quadrant now, this part. So where X will be still positive, bigger than 5. However, Y is less than 10 because it's lower than 10. So all the values, yeah. So we look at this region, then we can come to the conclusion that what happens. So we can look if X is still bigger than 5, that's positive. When Y is less than 10, yeah, this is less than 1. So minus 1, that'll be negative. So this X derivative will be negative. Then Y derivative. Y derivative, so if Y is less than 10, but still in the first quadrant, because our population model, we're assuming Y, the population is always positive, right? So this is still positive, less than 10. However, when X is bigger than 5, this is bigger than 1. 1 minus something bigger than 1, so negative. So then we have positive times negative is negative. So then we know that X and Y's derivatives are both negative. So we write negative, negative. This is true for this second quadrant. That means X is decreasing, Y is also decreasing. So that arrow is still clockwise. So you can do this to each quadrant around this, around that 5-10 equilibrium point. So around this, then the next one, you can do a similar analysis. You will discover overall it is a clockwise flow of this will repeat, right? Because it's periodic solution, so it will come to the same point and then do another cycle. So that explains that for any periodic solution, the direction of the flow. So what is so useful about the constant solution? So you see the 5-10, especially this constant solution, relative to the non-constant solution, which is the periodic, right, moving around it. So we know these X values are changing for the non-constant solution. But for non-constant solution, X average, so X sometimes you see less than 5, sometimes bigger than 5. Suppose X is changing with time, but the average value will be 5. Yeah, this value. So you see the constant solution can tell us the average population of X. So this constant value 10 will be the average value of the Y, the pre-population, which is 10. So from the picture, we can see for this non-constant, right? It's not a fixed point. It's a non-constant solution. You see the Y value sometimes higher than 10, sometimes lower, yeah, smaller than 10. But So for one period, if we do the average, it will be 10. So this is what Volterra's law tells us. The average of non-constant solution is told by those numbers, constant solutions. So, okay, so it's just to see the relationship. So in this one, I can also draw another curve. Suppose we have another solution curve. And then we can do similar analysis. It's just another periodic solution. And using similar analysis, we can also look at a certain quadrant, right? To come to the conclusion that this second periodic solution is moving clockwise. So, of course, the solution will depend on which point it passes through and some initial conditions. So we can have a different solution if we have some different initial data. So that is, so which curve it is, depending on at certain time, the XY value. So for now, you just see some solution curves, understand the simplest solution curve will be the fixed points, right? The ones indicated here as a point, right here as a point.